but the work that I'll be presenting today was part of my doctoral work at North Carolina State. So a lot of my work occurs in the context of student modeling, which is designed to help adapt or inform adaptive and personalized learning for students. And so what we're trying to do here is we're trying to better understand and model and provide insights for different student learning phenomena and learning-related phenomena. But as we all know, many of these things are often very complex, and students manifest these characteristics and constructs in very different ways. So one exciting way to help analyze this kinds of data and provide insights for these constructs is through multimodal learning analytics. So another aspect of this work that I'm presenting is that it occurs in the context of game-based learning. So games are really unique because they provide a very exciting opportunity for students to learn in a really rich story world with an expansive set of characters and simulation underlying the game. And what's exciting about this is students really express themselves in a very unique way when they're playing these games. So multimodal analytics really has a huge opportunity here. So the goal of my work then is to create a predictive framework where we have a student population, a game-based learning environment, a set of multimodal features and modalities where we extract the behaviors that we're interested in, and then predicting different characteristics such as the performance of students on assessments, their engagement with the system, their motivation, interest, all kinds of interesting behaviors. So the three components of this work are multimodal learning analytics that I mentioned, multitask machine learning, which accomplishes the idea of predicting these constructs simultaneously, and then early prediction, such that we can do this at early points in student gameplay so that we can inform adaptive systems to provide support. And so a key consideration that many of us have asked is the following scenario. So let's consider one student population, a game, set of modalities, and then let's say you have another student population, game, set of modalities. Maybe it's the same, maybe it's different. This happens all the time. Many papers have the same scenario. And maybe we have a different set of variables that we're interested in predicting. A key question that comes up pretty often in our community is then, how do we avoid starting from scratch each time we create a predictive framework? How do we share information from one of these contexts to another? And so I've only looked at a small slice of this problem, but I think it's a very important one. So in this work, it's in the context of Crystal Island game-based learning environment. So many of you might be familiar with the game, but I'll go into a little bit of detail in a bit. But we have two different data sets in this study. And there are many similar characteristics in the center of the Venn diagram here, such as the target variables, so post-test score and then student interest. And then the gameplay is the same because it's the same game, but there are key differences such as the student population and additional modalities that we have available. So to show the instantiated version of this framework, I know there's a lot going on here, but in the top of the diagram, it's Crystal Island sensor-based, where we collected student eye gaze, facial expressions, and then their game logs as they played the game. And we extracted these features and then created predictive models to predict their post-test score and their interest. And then in the second scenario, it's a different version of the game, Crystal Island Reflection, which I'll also describe in a bit, where we have a slightly different set of modalities, specifically their gameplay and textual reflections, but we're predicting the same two variables. And so the question is, as I've mentioned, how do we share information or avoid having to start completely from scratch when we create a new predictive model for the new environment or the new domain? So Crystal Island is a very interesting game-based learning environment that's pretty timely for microbiology education. So students arrive on a remote island where they're tasked with investigating a mysterious disease outbreak. And so they interact with characters in the game and read books, posters, all kinds of fascinating information to help them diagnose and then propose a treatment plan for the disease. And so the first set of, or the first study was in a laboratory setting where 61 college-age students played this game, and we collected, as I said, their eye gaze, facial expressions, and gameplay data. And so as part of this study, their pre and post data for microbiology was collected and measured, and then we also measured their interest after playing in the subject material. And then the second set of studies was done in the classroom context, where 118 middle school students played this game. And this was a slightly different version of the game where students were prompted several times during the game to provide their reflection on how they're doing and what they're planning on doing moving forward. And so again, in this study, we collected their pre and post data along with their interest. So to revisit the framework that I've described, now we know that the game-based learning environment is different, but there's many common features to it, the gameplay log that we collect. And then the modalities, there's some differences, but again, the gameplay is the same, so we have that shared feature. And then the target variables are the same, but the key question again is, how do we share information? And I'll get to that in a second. So for both of these data sets, we extracted relevant multimodal features. There's many features here that I won't go into detail, but you can find them in the paper and cited papers within that. But for each of the data collections, we converted the post-test score and then the interest score into binary variables, either low or high, based on the median values that we measured. So for modeling these target variables, we used random forest. The nice thing about random forest, at least in many implemented versions, is it supports both single-task and multitask machine learning, so it's an apples-to-apples comparison. So we used other common machine learning approaches, such as feature reduction and cross-validation for both tuning hyperparameters and evaluating the models. And for the experiments, we evaluated each possible combination of modalities, as well as the multitask version versus the single-task version. And then to measure the performance of these early prediction models, we used a metric called standardized convergence point to measure how early the models are able to accurately and predict, and how they're able to maintain that prediction throughout the sequence. And then F1 score for the classification accuracy. We statistically tested these versus baselines, and as well as for the early prediction component, we made predictions every 2 minutes in student gameplay, allowing us to have plenty of predictions per student. So to avoid death by numbers, because if you take a look at the paper, there are plenty of tables with the results, I'm going to go over some high-level findings from the first set of experiments. So in the first set of experiments, we evaluated multimodal versus unimodal and multitask versus single task. And so the highlight here is that multimodal data, or the sensor data and then the textual data, often provided extra context and ability to predict both interest and post-test score. In one case, for predicting interest in the sensor-based study, it wasn't as helpful, but it still can provide insight. And then for the flip side, for multitask versus single task, this interestingly was especially useful when predicting student interest, but not as much for predicting post-test score. For the second set of experiments, which were for transfer learning, I just want to briefly explain what I mean by transfer learning. So in the case for these two data sets, as I mentioned, we have a common set of features or modality in the gameplay logs. There are 130 features that are similar between the two data sets. So what we can do is we can learn a latent mapping or a latent representation of that modality and then apply it to new data sets as we achieve the data. So what this means, and it's very similar to using like a word embedding model where we've trained it on a large set of words and sentences and then apply it or fine-tune it to a new data set. So in this transfer learning setting, we used an autoencoder to do that and train it on the gameplay data from one context and apply it to a new one. And we compared 3 different conditions. First was no transfer, where the autoencoder was simply used to just reduce the gameplay data of the corpus. And then evaluate the models as they were for the previous experiments. And then for the two other conditions, the autoencoder was first trained on a source corpus, so one of the two data sets that I mentioned, and then either applied as is or fine-tuned on the new target data set. And then that data was fed into random forests for the multitask or single-task machine learning. And so for the experiments, for the high-level results for these experiments, we found two interesting results that were actually kind of opposites. So for when the sensor-based study served as the target data set, we found that when fewer modalities were available for that prediction, so for example, just gameplay was available, the prediction was actually outperforming the situation where more modalities was available. And then the opposite finding was true when the reflection data set was serving as the target data set. And so you might remember the sizes of these data sets really matter. So the reflection data set is about twice the size of the sensor-based data set, which can highly impact the transferability of, or the learned latent mapping when comparing these two. So we found that that really mattered. And it also speaks to the value of specific modalities, such as the text-based channel, which provided quite a bit of useful predictive information. To go over some high-level results of these previous few slides, for predicting both variables, models that incorporate more than one modality either in addition to or instead of gameplay alone were quite predictive and helpful for both of the constructs or measurements that we're interested in. Multitask models were especially useful for predicting interest, but not as much for post-test score. So this is somewhat of an interesting finding, but it speaks to the complexity of the constructs that we're interested in. Sometimes things are just harder to predict in general, so some constructs are just really related to the data that we're feeding in as input. So I think that's really one of the big factors in this case. And then for transferring information, we found that when we leverage information from one data set, it's especially useful. And perhaps a common or an intuitive finding is that when the data set's larger, it helps more in transferring. So in conclusion, multimodal learning analytics, multitask machine learning, and early prediction, especially used as a unified framework, are extremely powerful for student modeling and learning analytics, which can then inform adaptations or personalization that we would do to support students in real time. So for future work, there's so many ways that we could expand this. Some of the ideas include using more expressive representations of the modalities. There's always newer feature engineering techniques and models that ingest different modalities. Other kinds of modeling techniques, such as deep learning. We heard a little bit about neural networks before. That would be really useful to investigate. And then, of course, we talked about in the multimodal workshop the other day about looking at other modalities. So this can be another area of future work. And then closing the loop to be able to implement this in a real-time system and then provide feedback back to students when they need it and see how it affects their learning process. So I'd like to acknowledge all the people who helped out in this work in different ways, as well as ETS for supporting this work, and then funding, of course, and my contact information is available, and I'm happy to answer any questions.